We start our understanding of electricity and magnetism by first understanding the concept of electric charge. And in order to better get a grasp of electric charge, it's important to understand what Coulomb's law is. Coulomb's law essentially gives us a relationship between the electric forces between stationary charges. So let's dive into Coulomb's law by first looking at an example. Let's say that we have two charges, Q1 and Q2. And let's say these are opposite charges, so they attract each other. And we would know that in this case, the force felt between these two charges, so the force felt by Q2 as a result of Q1 would point in this direction, and the force felt by Q1 as a result of Q2 would point in this direction. And Q1 and Q2, it's important to note, are scalar quantities. We can denote each of these little vectors that we've drawn over here by writing them in this form. So this vector over here we'll call R21 hat, and this vector over here we'll call R12 hat. And they're pointing opposite to each other. Now, the force that Q2 feels from Q1 is given by a specific expression, and we can use Coulomb's law to understand this. So Coulomb's law says that the force, electrostatic force between two charges is equal to some constant K times charge 1 times charge 2 all over R squared. And if we plug in the values of the Coulomb's law in this case, then we get that, for example, if we want to find the force on charge 2 as a result of charge 1, F2 is equal to K times Q1 times Q2 over R12, which is the distance from charge 1 to R2, charge 2, excuse me, squared, times the direction that this force is pointing in. So of course, we know that this charge 2, is being attracted towards charge 1. So the force is pointing in the direction of the R12 hat vector. So we can write this as K Q1 Q2 over R12 squared times R12. Let me write that in a different color so it makes it a little bit more clear. R12 hat. All right, so now that we've understood that, it's important to take a note that the force Q1 feels as a result of Q2 can be better understood by Newton's third law. So the force that particle 1 feels is equal in magnitude, but opposite in direction to the force that Q2 feels as a result of Q1. So F1 is equal to minus F2. And we can write this again by just popping in a negative sign to the value that we have over here. So negative KQ1 Q2 over R12 squared times R12 hat. In this case, we have to write, excuse me, R21, because we're pointing towards the direction of Q2. Remember, once again, if that's not entirely clear, force is a vector quantity, which means that we have to give a magnitude and a direction. So this is the magnitude over here, this quantity over here that we have in both of these cases, and this gives us the direction. This gives us the direction. So it's important to take a note of that. All right. So now let's look at a simple example that kind of ties this concept together. And let's say that we have two charges. So we have two 1 Coulomb charges, and they are 1 meter apart from each other. And we want to find the magnitude of the force between them. So how do we do that? Well, first of all, we know that force is equal to K times Q1, Q2 all over R squared. So if we plug in the values, we know that K is just approximately 9 times 10 to the 9th. and then Q1 and Q2 are each 1 Coulomb. We divide that by the distance between them squared, so 1 squared. So we're left with 9 times 10 to the 9 newtons. Very simple example, very easy example. And it should kind of help you understand these concepts at a more simplistic level. But of course, things are about to get more complicated. So let's take a look at a system with more than 2 charges. And these systems where we have more than 2 charges are known as discrete charge distributions. Discrete charge distributions. So let's pictorially represent this. It's a fancy word, but it's really quite simple. So let's say we have some charge Q over here, and let's say we have another distribution of other charges. So we have Q1, Q2, Q3, all the way up to some charge Qn. And we want to find the net charge on Q as a result of all of these n charges. In order to do this, we sum up the forces due to each charge vectorially. So Q1, let's say, is a like charge to Q. We would find the force as a result of Q1 on big Q. So that's in this direction like this. Q2, let's say it's an opposite charge, then the force would point in the same direction as Q. And we add up all these vectors until we get to Qn, and that would tell us the net force on Q as a result of these n charges. So in order for us to mathematically represent this, we can say that Fq is equal to K times Q times Q1 over R1 squared times R1 hat, right? Plus K Q Q2 over R2 squared times R2 hat, plus all the way up to K Q Q over Rn squared times Rn hat. And what this is known as is the principle of superposition. Once again, a very fancy statement, but it really just means that we take the forces as a result of each of these individual charges on Q, and we add them up together in order to find the net charge. So in words, we can write this. So in order, let me use a different color once again. Let's go back to, actually, let's use red. So in order to find the net charge on Q, let's scroll down, due to n charges, oh, excuse me, not the net charge, my bad, the net force on Q due to n charges, we simply sum up the forces due to each charge. We do this vectorially. And that's known as the principle of superposition. Now we've come up with this equation over here. F sub Q is equal to this funny business over here. Let's write it in a cleaner form. So we can actually use sigma notation in order to represent this better. So we can say that F sub Q is equal to the sum from I is equal to 1 to n of K Q Q over Ri squared times Ri hat. How does this make sense? Well, starting at I is equal to 1, so K Q Q over R1 squared times R1 hat, that matches the first part. Then we go to I is equal to, so KQQ over R2 squared times R2 hat. So we sum that with the previous value, and we keep on going until we reach the nth value. So we get this. This is a nice, cleaner representation of the same thing that we wrote over here, just in summation form. So why is this useful? And in order to better understand this, we have to consider that we have a continuous charge distribution. So for example, let's say that we have Q, so charge here Q, and we have this body, looks something like this, and we want to find the force felt by Q as a result of this body over here. And so one way to think about this is a more simplistic version of what we have over here. So what we can do is we can chop up this body into little tiny pieces. So each of these pieces can have volume dV. So that very annoying line there, right? So we have each little tiny cubic portion, which we call dV. And we know that the charge of each of these little tiny bodies, Qi, is equal to the charge density times the little tiny dV volume. So we can chop up this body into an infinite number of charges with a volume of dV. And we can sum up the total contributions of each of these little tiny dVs, and we can arrive at the net force on Q as a result of all of them together. And once again, to be clear, we know from previous studies that rho, the charge density, is equal to the charge over the total volume. So in order for us to find the charge of each of these little tiny pieces, we multiply both sides by the volume. So we get the surface charge density times the volume is equal to the charge. So that's what we did over here, that we took surface charge, the charge density, and multiplied it by the little tiny fragmental volume that we have over here. And so if we want to represent this now, using this equation that we wrote over here, all we have to do is say, okay, well, let's just substitute the numbers. So F sub Q is equal to summation from I is equal to 1 to N. So we have N charges times K times Q times rho, excuse me, I wrote a P, should be a rho times delta VI, small volume I, over R squared, which is a distance from Q to whatever that little tiny volume is, times R hat. And a little thing to make a note of here, R hat is the unit vector from delta VI to Q, and R is the distance from delta VI to Q. Now, if we take N to infinity, so if we take N to infinity, so that means delta V becomes dV, and N goes to infinity, we know that F sub Q then can be written in an integral form. So the integral, oops, sorry, K Q rho dV over R squared times R hat. So now, if we have the volume of the charge, this is the volume charge distribution. All right. Now, what if we have like a pancake-like charge distribution? And let's say all of that charge is actually distributed on the surface of that, that little pancake-like structure. How would we make sense of that? Well, now we use surface charge density. So now we can say that F sub q is equal to integral of k times q times sigma times dA all over r squared times r hat. And what sigma is, it's the surface charge density. So that's equal to the charge over the area. So all I did was, in order to find the charge, I said sigma times area is equal to charge. I just substituted that value over here. So that gives us the surface charge density. So that's the net force felt on Q. Now, what about a linear charge distribution? Well, for linear charge distributions, the F sub Q is equal to, same thing, K times Q times lambda dl over r squared times r hat. So notice that all we're doing when we're going from a volume charge distribution to a surface charge distribution to a linear charge distribution is we're just changing the value that we put here. And that's completely dependent on what type of charge distribution we're dealing with. And once again, we know that lambda is equal to the charge over the length. So we multiply both sides by the length, and we can substitute whatever we get for the charge over here. Just to talk about units a little bit, we know that the unit for rho is Coulomb per meter cubed. Units for sigma are coulombs per meter squared, and the units for lambda are coulombs per meter. Now, let's consider an example by putting all of this together, and let's try to neatly tie all of these concepts together so that we can focus on understanding the key core aspects of this. So let's take a look at an example. So let's say we have a force on a test charge due to a uniform line of charge. So consider a force on a test charge Q due to a uniform line of charge. So if we want to find the net force as a result of this uniform line of charge, we have to use all of these concepts together and make sense of this. So first of all, let's draw our uniform line of charge. This is our uniform line of charge. So let's say that this charge Q is over here. Use a black color. Charge Q is over here. Let's take the little portion of dq. All right, so what we do in this problem is we take each of these little fragmental pieces, dq, and we find the force that they exert on Q. And then we sum up all of those forces vectorially, and then we can find the net force on that charge. So first of all, what I did over here was I put a little dq, and that represents this little tiny piece of along this length. And so if we know that the total charge Q is evenly distributed over this length L, this is the length of L, we know that dq is equal to lambda times dx, right? So now all we have to do in order to find the force that dq poses on Q is as follows. So dF is equal to kq times dq over the distance between dq and q. So we'll call that r squared. Let me just draw it. This is r. And so, and that's in the r hat direction. Now, when we integrate this, so when we integrate this value over here, we know that r squared and r hat will change. So we need to wrap both of them in the same variable. So first of all, let's focus on r. So r, how can we write that? Well, we know that if we establish this distance as a and this distance as x, x will change, a will remain constant as we move from dq to dq to dq along this line of charge. So r is just going to be square root of x squared plus a squared, the Pythagorean theorem. R hat will be, let's see, so we know that r hat points in this direction. And so we know that if we break this up into components, r hat is equal to, doing this in my mind, negative x sine theta, this angle is theta, negative x hat sine theta, sorry, minus y hat cosine theta. And so we know that sine theta is just equal to x opposite over hypotenuse, x over r. And that's equal to x over x squared plus a squared, square root of x squared over a squared. That is equal to, let's see, so now we look at cosine theta. Cosine theta is equal to a over square root of x squared plus a squared. All right, there we go. And so now we have everything in terms of a and x. All of these values, all of these values that we got over here can be substituted into the original equation. So we know that now df is equal to, let's see, so kq will remain the same. Those will not change. Times dq. So dq is just lambda times dx. We know that already. Over r squared. R squared is simply this value over here squared. So x squared plus a squared times r hat. R hat is what we have over here. So we reduced it to negative x hat times this business over here minus y hat times this business over here. So we can just write this as negative x hat x over the square root of x squared plus a squared minus y hat times a all over square root of x squared plus a squared. All right, so now if we simplify this, we get that this is equal to negative kq lambda times x hat plus a y hat all over a squared plus x squared raised to 3/2 dx. Now we can integrate this. So force F, net force, is equal to the integral of dF, which is just the integral of this thing over here, this very scary looking thing over here, negative kq times lambda times x hat plus a times y hat over a squared plus x squared raised to 3/2 times dx. And what are our limits of integration? Well, if this is x is equal to 0, if we establish this as x is equal to 0, then this is x is equal to negative L over 2, and this is x is equal to L over 2. So we integrate over this part. So our limits of integration are x is equal to negative L over 2, and x is equal to L over 2. And so now I won't actually resolve this integral for you. You can actually use a table of integrals to find what this value is. So I'll just resolve it because I've done this beforehand. So this is just negative kq lambda ay hat x over a squared times the square root of a squared plus x squared from negative L over 2 to L over 2. And so now what do we do? Let's see. So we now plug in L over 2 for every place that we see x. Let's see, we get negative kq times lambda L over a times the square root of a squared plus L squared over 4. And we know that this value over here, lambda times L, is just q. So we can rewrite this now as equal to negative kq times q over a times the square root of a squared plus L squared over 4 times y hat. And so we know that the final value, f sub q, is equal to negative kq q all over a times the square root of a squared plus L squared over 4 y hat. There we go. So that's the final value. It's that simple. Oh, and one important note that I wanted to give over here is that this goes to 0. X times x hat is 0. They point in the same direction, and so if you take the dot product, it's just 0. All right. So now finally, I want to talk about one last concept if we have time, and that is the energy of a system of charges. So let's say that we have two charges, Q and Q over here. Distance between them is R2, and we want to push Q1 such that it's a distance of R1 from Q. Let's suppose that Q is at the origin, and we want to find how much work needs to be applied to move Q from R2 to R1. Now we know from mechanics that, so let's draw this to represent the distance between Q and Q, that work is equal to the integral of the force applied times ds. So we're moving from R2 to R1. So our lower bound of integration is R2, our upper bound of integration is R1. And the force is F applied in this case. And so we know that F applied is actually just the opposite of force Q. Opposite of the force Q that it exerts on Q. So we know that FPP is equal to negative FQ. So it's a force pair of FQ, and that's equal to negative KQ times Q over R squared times R hat. And R hat is radially out from Q. So it's in this direction. This is R hat. Anyways, I think that's a fairly thorough understanding of sections 1.1 through 1.5 of Electricity and Magnetism by Purcell, third edition. It's important to say that you should still consider trying to read the textbook by itself, although this is a condensed version of everything that you need to know from 1.1 to 1.5. Anyhow, there were some tricky integration problems, examples that we looked at, but we were able to solve them. Eventually, as we move on to further study of electricity and magnetism, the foundation that we establish in these introductory videos will be increasingly important. So it's important to understand every single concept in this video before you move on further. Anyways, that's all from my end, and we'll pick up from next time with the next video. Until then, thank you so much. Keep studying physics and keep looking at the stars. Thank you.